Hello. Thanks for coming in. And let's see. Let me figure out how the clicker works. Great. 2 buttons. Hi everyone. I'll go a little fast because it's a longish presentation, but you could always just come up to me. I'm friendly. I'll answer your questions if I can. So we're going to be talking about formal reasoning to build subtle systems in Go. Show of hands, who's heard about formal methods or formal reasoning? Cool. Yeah. I wouldn't have answers to your questions. Yeah, so a little bit about myself. I'm an engineer at VMware. I work with the kernel and the driver team. So not a lot of Go there, but when I am using Go, it's generally for my own personal projects. And I'm just so interested in the concurrency primitives that are such first-class citizens in the language. And that's kind of why I think formal reasoning is such a good such a good way to reason about your Go system specifically. So what I will be, so I'll set the expectations of the talk a little bit. I'll be talking about the basics of formal reasoning. I'll be talking about what thinking above your code, above the implementation, and looking at the intent of your code means and why it's important. That's sort of the genre of the talk. I'll be talking about the examples of formal methods being applied to Go concurrency problems, and some examples of formal methods used in production. Right? What I won't be covering is the in-depth language specification details, and in this case, the language that I'm looking at is TLA+. So first of all, software is everywhere. And I was able to find this really scientific graph on the internet, which was as the number of Gophers increase, the number of projects goes up pretty exponentially. And with this, with increasing number of projects and the increasing size of your projects, it gets, especially if it's like very mission critical, a lot of subtlety involved, not easy to reason about in your head, reliability becomes a really important factor. And reliability is especially hard to reason about. Yeah, so projects get complex very quickly, right? The more developers you have, the different styles of coding, there aren't really a lot of standards for this, right? Often something as artistic as software is difficult to reason about. There's so many standards, people have preferences. How do you standardize any of this? Right? So also, you have legacy software, which has barely any documentation. Trust me, I know. Also, just entropy, right? So the longer your project is out in the wild, the more chinks in its armor, so to speak. So how to think about your software? You want to think about what you want it to do before the how. And either informally or formally, writing down the expected behavior is kind of what the big idea is, right? So what it finally comes down to is how do you ensure that your system is designed in a way that that doesn't crash or reach states that are incorrect. Incorrect depending on how you define what incorrect means. This is a great quote by an American cartoonist, Dick Quindon, which is, writing is nature's way of telling you how sloppy your thinking really is. And this is one of his comics, How to Steal a Car. Definitely check out his work. It's hilarious. But now coming to the thing that's interesting to most Gophers, right, which is concurrency. When can you have concurrency? The simplest example, if you have multiple systems that are running independently and have some shared global state, you have concurrency. And with concurrency comes non-determinism. So 2 executions of the same program with the same input can produce different outputs. And what's an example for that? Well, the very common one is the readers-writers problem. If you just switch around the order of who's writing when and who's reading when, you can have all sorts of different behaviors. So this is an example of non-determinism, which is difficult to reason about in any sort of testing way. Yep. Let's look at a simple example. I don't know if you had this example back in school, but I did, which is design a banking system. And even with such a simple monolith architecture with just a front end, a back end, and a database, there's like 2 points of concurrency already. Say, this is the system, right? You want person A to be able to transfer money to person B. So you need to be able to check if person A has sufficient funds. You need to be able to add the amount to person B's bank account. And you need to be able to deduct the amount from person A's bank account. What happens if one of these processes fail, right? What if your check balance fails, or you add the amount to B and you never deduct the amount from A? Well, you have free money, that's one advantage, but it gets harder and harder to write tests for this. So just in this simple system, you can have a bunch of races, crashes, partial failures. You could be like, hey, let me just write unit tests to solve this. But the thing is, even if you say the number of simultaneous transfers is n, if you had to write a unit test for every possible behavior, that's how many unit tests you would have to write just for 3 transactions. And that's the formula to calculate that. So what's the alternative? You can write formal specs, and we'll discuss what that is. But I hope you're getting kind of the why of why you would want to do something like this, right? And this is from Lamport's talk, because I couldn't figure out a better way to represent this. But say you're designing something as simple as a shed. Generally, a rough sketch is enough. You can write a rough sketch on your piece of paper, and you can start building your shed. What if it's something a little more complicated, like a house? Then you maybe need a little more technical documentation, right? And if you're building the Golden Gate Bridge over there, you need multiple teams, phases, really, really technical documentation that's changing all the time to build something like that. So using this analogy, from very simple to very complex, where does building concurrent or distributed systems lie, right? Similarly, if it's, I don't know if you can see that, but if you have like simple code, just a simple function, generally just writing a bunch of comments work, right? But if it's something with a little more subtlety, something that's not obvious when you look at the implementation, maybe a document, maybe some longer comments, maybe some mathematical prose. But when you're designing concurrent or distributed systems, you would want to write in some formal way which is not open to interpretation and is telling you precisely what your system is doing. And the advantage of doing that is that you have access to tools. So you can actually use formal tools to check if your formal specification is correct. And we'll see what that means. So how can you model programs? You can model them in a number of ways. You have Turing machines. You can model them using automatas, programming languages. But the good news is you can describe any program as a state machine. So this means that you can describe your program as a set of behaviors. And what does a behavior mean? A sequence of discrete steps that your program can take. So this requires us, if you guys remember from automata theory, for you to define an initial state and the next state of your system. What are the rules for you to go into the next state, right? And what can your next state lead to? What are the further states that your next state can go to? And often, from an initial state or the current state, you can have multiple next states. So you, I think this connected to my laptop. Yeah, so you can have multiple next states. So you have sort of a disjunction of next states, right? So you can you want to be able to model this non-determinism, right? You can go to any of the next states non-deterministically. So this is how it would look like. Say your initial state is hungry. What are the possible next states? You could order a pizza. You could order biryani. You could order currywurst, which I still haven't tried, by the way. So if you guys have recommendations, please let me know. But basically, this is just a bunch of, so you can write this as pizza or something, right? If you want to be fancy and mathematical about it, you can use the disjunction capital V operator, right? And you'll see this in the specs that I'm trying to show you. So TLA plus actually gives us the framework to do this, right? But what is TLA plus? Well, it stands for Temporal Logic of Actions. It was developed by Leslie Lamport, who was also the Turing Award winner in, I think, 2013. And I think he developed this back in 1999 after like several decades of research and modeling languages, concurrent systems. He has a bunch of amazing papers that you should check out. He also created LaTeX, if you didn't know that. Yeah, so what does temporal in temporal logic means? It means that you can model stuff like, model timing behaviors. So stuff like, eventually something will happen. Eventually a process will receive a message. Or after a certain point of time in your program, a property holds forever. So these are things that's interesting to a Go developer when they're designing concurrent systems, right? And TLA Plus and other many modeling languages let you do that. So let's look at a simple example. We have Euclid's algorithm to find the greatest common divisor. Even if you don't know that, that's fine. This is what the code would look like, right? Basically, you have some condition which leads to some recursive arm in this case. So this is kind of like our non-deterministic example. Depending on the input, you can either go into the first block or the second block. So how would you start defining this formally? As a formal specification. Let's see if we can use the rules that we were just talking about. This is what a simple TLA plus spec looks like. And all I need you to focus on over here is the init and the next state that we have already mentioned, right? So what is it doing? Your init state is checking if x equals some constant m, and y equals some constant n. Now, it's important to see that this is not assigning those values to those variables. It's checking if those values are true at the initial, and your state is the initial state, right? And if both of them are true, since it's a conjunction, then your init state is true. And your next state also has these two arms that we were talking about, the if and the else case. So if x less than y is true, that predicate holds true, and then you can start checking the next predicates. So over here you have y prime, which is just the new value of y, equals to the old value of y minus x. Again, this is not an assignment, it's checking if that's true. If you have reached the next state, that predicate should hold true. And also this curious thing, which is the new value of x is not changed, right? This is not something that you do in programming languages. You do if a variable is unchanged, it's not something that you're terribly interested about. But another thing is, what if you remove this line, right? What if you don't have that line in the spec? Say your x prime from an integer becomes a string. According to this spec, that's allowed if you remove that line. So you need these kind of explicit sort of predicates mentioned in your specification. So TLA Plus is a language that lets you write specifications formally. And formal specs are required if you want to apply tools to them. And what are those tools? Well, model checkers, again, this is a very small part of formal reasoning. Formal reasoning has a bunch of things, but I'm talking about model checking. So model checkers verify the correctness of the spec that we just saw. And how it does that is it runs it against all possible executions of your program. So internally, it builds a state machine of your specifications, and it basically checks whatever rules that you wanted to check for, right? So more specifically, model checkers verify your system using induction, or by enumerating possible states your system can take on. Right, so for example, if you want to check for all integers, you wouldn't want to check for every single integer because that's not possible. You would check it for an arbitrary integer, and that's enough to sort of reason about, you know, that set. Yeah, and you're showing that for none of the possible states of your system, your properties that you want to remain true are violated. These are called specifications. So model checkers can do two important things, which is it can check liveness and it can check safety. Basically, liveness is good things happen. Safety basically means bad things won't happen for any state of your system or any finite execution of your system. Interestingly, liveness actually means good things eventually happen, and that's where the temporal from temporal logic comes in, right? So like the previous example was, a process will eventually get a message. What does safety look like then? Like I said, it's a finite set of states, should not violate some property. If that's the kind of property that you're dealing with, it's probably a safety property. These are some examples. Two threads can't be in the critical section at the same time, for example. And actually, these properties are a further subset of your safety properties called invariance, which means that no particular state can violate your property. This is fine. This is not too important, but it's nice to know. Liveness, again, is just every message is received at least once by a client. That's now, how would you try to write a test for this? Because to prove that this is true, you would have to prove this for an infinite amount of states that your system can be in, because at least could mean any time in the future, right? No finite sequence of steps can break this property, because even if the message is not delivered now, it can be delivered sometime in the future. So you need an infinite sequence of steps to break this. So I hope you can see why you would want to, one, prove that this is true for your system, and why it's very difficult to write tests to kind of ensure that this behavior is true for any system that you write. So yeah, no point in the future does it ever become true. So let's look at how we can use the things that we've learned so far to debug an actual Go concurrency problem. And the bug that I'm going to show you was actually found in the Go PS library. It was a nasty deadlock situation that was happening. This is the issue, and I've linked to the issue at the end in my references. And this was the problem code. It's the find all function. You don't need to look, you don't need to read through everything. I have annotated the stuff that you have to worry about. So first, you have the unbuffered and the buffered channel. The buffered channel is the more interesting one, the limit channel that is called. And what it's doing is something called limited concurrency. So it's ensuring that only a certain number of Go routines are ever spun up at once. And how it does that is by tokens. So in this next for, in the for loop, the second line, you can see that it's adding a token into your limit channel. And as soon as your limit channel becomes full, you can't spin up more Go routines, right? And then it spins up the Go routine, the Go func, and you have a defer func where you're releasing that token, which means that I have ended. Here is my token back. New Go routines can be spun up. Found is interesting. I mean, because P is basically any processing that your system is doing. It saves that in that value P and puts it in the found channel. Now, what happens if your limit channel is full, right? So when your limit channel gets full, that your for loop gets blocked on the second line where it's trying to add that value in your limit channel, right? And since that for loop is blocked, it never reaches the for loop down below, right? So no one is reading from found anymore. And since it's an unbuffered channel, nobody is able to add to found anymore. And since nobody is able to add to found anymore, that defer func never runs. So there's a bunch of Go routines that are trying to add to found, but which are not releasing their tokens because it's blocked in this for loop over here. Subtle bug, but the fact that this was in production code, it's interesting. So Hillel Wayne, whose blog I have linked to, by the way, he has a bunch of tutorials on TLA Plus applied to like Go programs. Check them out. So he actually demonstrates this bug by writing his TLA Plus spec, and your model checker can interestingly show you the exact trace of the states that your program took to reach that deadlock condition. And he finds the deadlock condition. The model checker tells him exactly how it reaches the deadlock condition. This was the spec. You can go through it later on when you have the time, but I won't go through it. This is more interesting. This is the model checker output. And this tells you exactly what states led to the deadlock condition, the thing that I was just explaining. And what he did was make the fix in the TLA Plus spec. So instead of deferring the release of the token, he releases this token as soon as the Go routine is spun up. And he runs the model checker, and it passes the model checking. In fact, I think the fix that went into it was kind of similar to what he tried on his TLA Plus, but correct me if I'm wrong. So let's try designing our own concurrent system, right? And we'll do it right. We'll first design the spec, and then we'll worry about implementation if we have to. It's a simple concurrent system. It's a simple pipeline, 3 steps. There's an input. So your input is basically something that's handling some incoming data and adds the data into some shared queue. And whenever it adds the data into the shared queue, it also adds an event in a separate event queue. So saying that, hey, there's new data available in the shared queue. Whoever reads the event now knows and knows to check. Step 2 is the processor, which receives this event on the event queue, and it can check if there's there's new data available in the shared queue. And thirdly is just some processing on that object that was added in the shared queue. It can be pruned away or whatever. So let's see how that looks like. You have your first process. It's adding data into your events queue, and also adding the event into the event queue and adding the data associated to that in your shared queue. And your second process is receiving that event. It's like, hey, there's a new event, I need to check the shared queue. And then finally, some other process can prune away the data. Now, the next few slides, if you're not used to looking at specs, it can be a little jarring. So you don't have to worry about this spec. Just look at the things that we've already looked at, which is the init condition. It's a little more verbose, but basically is just initializing your queues. It's talking about what the initial values are in your event queue and your shared queue. You have your type invariant. So if you remember invariance, it's basically checking that no matter what the state of your system is, your incoming queue should only have IDs belonging to that sequence set, or those kinds. So it's checking type for every possible state that your system can stay in. Now, I've underlined the things that are important. Actually, this line is also important, which I fixed in my presentation, but we aren't using my laptop. So the first line is receive incoming. So the first underlined line over there, incoming prime, which is a new value of incoming prime, is basically should be equal to the old value of incoming, the queue, plus the ID appended to it, and also the shared storage, the new value of shared storage is. So this is a cool way of managing addition of values to your queue. So it's just marking something as occupied. Initially, the value was vacant. Now it's occupied, which means that some value was added to the queue. And your receive incoming gets the value from the event queue and then checks if that value was actually added in the shared queue. Again, ignore this if this makes you queasy, because it makes me queasy. But yeah, so basically, you're also modeling stuff like your process waiting, you're pruning your object and stuff like that. This is the important bit, which is, at the end of the day, it's still the same spec. You have your next, which is a disjunction of the bunch of things that you have just, written, the specs that you've just written down on the previous page. And your entire spec is essentially make sure that for any state my system is in, init and next should remain true. That's all that it's doing. And it's checking it against the type invariant. So you can run your model checker, and you'll actually see on the bottom right that it tells you that a deadlock occurs over there. And if you follow the trace, you'll be able to tell how exactly the deadlock happened. And the problem was this sequence of steps. Step one is processing the input. It's adding to the shared data. And after it has added that shared data, it is adding the event associated with the shared data. Some of you probably already know what's going to happen now. Step two, you've already pruned the object that was added in your shared data, because it was added before the event was even added, and the object is removed. And then after the object is removed, your step two receives the event that there's a new object being added. So there's like this nasty race condition that's happening over here. But alas, there is no objects in the shared data. So now your step two is waiting for some object being that's going to be added to your shared queue, but there's nothing that's going to come there because step one thinks that it's already done its job. So there's a race between step one and step two, adding the object and adding the event, and your step two pruning the data before handling the event. The fix is simple. You just remove that layer of concurrency. Don't let your first process do those two things. Instead, you should just only put the identifier on the queue. Let step two worry about adding the object after it receives the event, right? So what does it look like? Step one adds the event. Step two receives that event and adds the object to the shared queue. And now there is no concurrent behavior happening where you don't have like a happens before edge between these two processes, essentially. So now you have that. So how would you fix that in your spec? You just move that line down. The line that where you're adding the shared queue, you're just moving it down, and your second step is worrying about marking that as occupied. You run the model checker, and it runs. There's no deadlock anymore. What's interesting is that within 8 seconds, it was able to check 900,000 states that your program could be in, and this is just for 3 objects that were added in your shared queue. So it does a lot pretty quickly, right? So before I come to that, if we had simply implemented that system, you would have a weird intermittent error that you would have to worry about for weeks before realizing what was happening. But if you write the spec first, check what you're doing, and then start implementing, you, especially when you're dealing with complicated software, there's a guarantee of expected behavior. So was that relevant to any actual systems? Is it just a toy? Is it only useful for toy models? Let's try to drive that point home. Who uses this in production? Well, Amazon is one of those companies. In fact, they wrote an entire paper about it. This was the paper which I've linked to towards the end, my references. And what they say was, and this is 2014 data, they use TLA Plus for more than 10 of their complex real-world microservices. And for every case, they were able to add significant value. And they were able to prevent subtle bugs that hadn't even reached production yet. In fact, they were also able to make aggressive optimizations just by changing their specs first, seeing if it's still correct, and then implementing the optimization in their systems, right? In fact, they have an entire group, automated reasoning group. I know a lot of other companies have it as well, but so that's the link. You can check them out as well, and they're doing some cool stuff. Apparently, solving century-old problems using automated reasoning. I haven't read it, but I'm intrigued. So yeah, thanks for making it this far, and let's try to conclude. And again, I'm going to borrow from Lamport because I think he said it best. What do programmers need to know about thinking about your code in this way? Everyone thinks they're thinking, but if you don't write down your thoughts, you can really go wrong. There is a need to think before coding, and there's a need to write before you code, because any code that someone is likely to use or modify needs to be specified. Because most importantly, that somebody could be you next month. There's importance in specifying everything you code, and if required, how it does it. And you should always try to specify your code above the code level, in terms of states and behaviors and input and output functions. And thinking mathematically provides a rigorous way of doing this, in precise terms, being as unambiguous as possible. Disclaimer, finding bugs is not the function of writing a formal spec. It's better to write the spec first, tease out your thoughts, and then start implementing after the model checker tells you, cool, we have proved that your system is going to work how you intend it to work. Because writing formal specs isn't intuitive. Like I showed you in our previous example, it's hard work. And we're generally used to implementing the how and not the, we're generally not used to implementing the what of the system, but the how. And even if this talk doesn't apply to you, right? Even if you never write complex critical systems, learning to write formal specs helps you write informal specs that you need to write anyway. Because once you have some practice with writing formal specifications, now every time you write a document or every time you write some comments, you're writing it in terms of behaviors and states that your system can be in, which is much clearer to write. Also, you can trace out the possible states that your system can be in and reason about it, what exactly is going on in your system. And also, it provides a great way to document your systems in precise language that is not open to interpretation, right? If you write a spec for your system, you give it to your manager or your customer or client, they know exactly what this system is going to do because it's all there in math. Well, yep. Thanks. These are the references. And if you want to go through them, please do. The first one is the lectures on TLA Plus spec. I have linked to all the papers, the articles, the image references. I use Gophers liberally in my talks, and René French is the original author, and of course, a bunch of other great creatives that you should check out. I didn't have the idea of adding the QR code, which seems so amazing to me. But yeah, I mean, the slides are in my speaker deck, which you can check out and then click these links. Thanks a lot.